One of the next species we're going to be spending a little bit of time with is the free radical. So it's useful to compare the free radical to cations and anions. So we'll just look at the methyl free radical versus the methyl cation and the methyl anion. The hybridization of methyl cation is sp2. That's also the hybridization of the methyl radical. The methyl anion is sp3 hybridized. And so if you look at the geometry of this, the sp2 hybrid orbitals are arranged as a trigonal plane on the central carbon, and then there is a p orbital that is perpendicular to that central plane, and there is a plus charge on the carbon. The free radical has the exact same arrangement of orbitals because it's also sp2 hybridized. Except this time, in the p orbital, it's not empty. There is one electron in the p orbital. For the anion, which is sp3 hybridized, the orbitals are arranged in a tetrahedral fashion, and I'm just going to show explicitly one of the sp3 hybridized orbitals. And this one has a lone pair of electrons in it. The important thing to realize about both the radical and the cation, both of these are electron deficient. The cation, of course, desires to form a bond with something that has two electrons. A free radical wants to form a bond with something that has one electron. All of the same electronic factors that stabilize or destabilize a carbocation will behave the same way towards a free radical. So, for instance, I can stabilize the free radical by resonance in the same way that I would stabilize a carbocation by resonance. Stabilizing the carbocation by resonance, the pi electrons move to form a new pi bond. The carbon that lost the electrons gains a positive charge. For free radicals, it's a little bit different how you draw the arrows, because instead of drawing a normal double-headed arrow, now you're going to use something that's called a fishhook arrow. So the electron on the end carbon is going to form a new pi bond with one of the electrons from the current pi bond, and meanwhile, the carbon that doesn't do the bonding ends up with a radical. So it looks like this. So I can stabilize a radical by resonance. I can stabilize a radical by hyperconjugation. So a CH3 radical is less stable than a primary radical, which is less stable than a secondary radical, which is less stable than a tertiary radical. So this is less stable, more stable, because there is more hyperconjugation.